Thank you, Anup. My name is Srini and I work for NetApp. I'm going to talk about it's not Oxymoron, it's not Oxymoron. Okay. So it's on computing on encrypted data. I mean, you may wonder, why is he talking about computing in a storage conference, right? But it's still about data, okay? If your data is coming in encrypted, you can do nothing with it. It's a blob of data. You can do really nothing. You can't do deduplication, compression, analytics, machine learning, everything falls flat, right? So you can't do anything. So what happens if you encrypt the data? How do we even handle that? Okay, that's the topic for today for me. So let me quickly run through the introductions. So who am I? I am an engineer with the Advanced Technology Group at NetApp. I'm working since 2011 with them. I spent a decade working on security before joining NetApp, mostly on trying to get a PhD for 5-6 years, and I got it initially. And then several years at RSA Security. So pretty much security for about 17, 18 years now. At NetApp, I do work on data security and privacy. I also work on erasure codes. I work on distributed storage systems. I mean, I don't get into the details, but I just use distributed systems for testing my erasure codes and other things. About my involvement with SNIA, I gave a talk last year at SDC on erasure codes. Some of you might have. How many of you attended my talk last year? Thanks for you guys, because I got a great feedback from you guys, and that's what actually motivated me to submit this talk at all, okay? So thanks a lot. And I gave the same talk at SDC US as well. I'm a member of SNIA Security TWG, Technical Working Group. Mostly what I do is I try to stay awake at 2:30 a.m. because that's when they have these weekly meetings. Apparently people are all over the world. They are from Australia, Singapore, UK, US, everywhere, okay? And an early version of this talk, I did present what I'm going to speak about. I did present an early version of this at a data storage security summit last year. About the talk, it's on something called a searchable encryption. Okay, so if you want to go back and then look up more details about what I'm speaking here, you'll have to search for this, okay, searchable encryption. So there are encryption technologies. So mostly all companies say that we do support encryption, we do have security inbuilt in our storage device. And what do? They switch on encryption, they use some crypto library, they use AES. Or maybe if they're going to transfer data from one node to another, they're going to switch on SSL, which means you're going to use some RSA algorithm or something, that's all. So what is more than that? Okay, actually nothing. You just have to switch on all these crypto libraries and you're good to go. And companies do claim that your data at rest is actually very safe in our hands. What do? They encrypt the data there. What do you even mean by that? They switch on full disk encryption. Okay, which means at the fag end of storing your data in the media, they're encrypting and storing it. But you actually handled all my data in plain. You only encrypted to store it because if somebody lost the media, then it's safe. But you handled my data. And this is particularly important in this age of cloud and all, because your data is not resident on-prem anymore. It's going somewhere, I don't know where. Maybe it's in Singapore, maybe it's in US, I don't know. And the data has been used by the cloud service provider themselves, looking into what you're storing, what can I advertise for you? Okay, this guy just got a promotion. Or this guy just got a bonus. Why don't I advertise? How about some furniture for your house from Pepperfry? You'll have an advertisement right there. Okay, they're doing all sorts of analytics on your data, right? So essentially, they have all your data. There's no privacy for us, right? All our data. At the end, they're just storing it encrypted in the drive, which is essentially useless. Okay, who's going to steal the drive from Google's or Amazon's data center? Okay, that's pretty much useless. Okay, so what we are talking about is privacy for your data much before it even hits the cloud. Okay, the privacy being taken in your hands, the data owner's hand. Okay, so that's what we're talking about. And this is a topic which has not been there for like 50 years, like in erasure codes, or 20 years or anything. This is a brand new topic. 3 or 4 research groups in the whole world works on this area. I would say there is not even a single PhD which came out of this area. Okay, it's a brand new topic. I'm 100% sure that you cannot listen to the same talk anywhere else. Okay, provided those professors who work in those two or three groups talk. So what am I going to present to you? It's going to be a lot of mathematics. I'm going to give you a brief introduction to linear algebra, abstract algebra and all, and then I probably give you some algorithms, how AES works, how the searchable encryption works and all those things, which will probably go way above your head, and I'll be like, that's exactly not what I'm going to do. It's going to be a non-mathematical, non-algorithmic talk, way basics. I'm going to start with very, very minimum. I know that I'm talking to a storage audience who just had a boxing match here about NFS connector and this one, and I don't know, I have no idea about what they spoke about. So I'm going to go to the real basics. Okay, start with something as simple as you have a user and you have a cloud. How do you encrypt the data? Starting from that, so there's no prerequisites for this. So what's an oxymoron? So oxymoron, I'm sure everybody knows it, but I thought I'll just put it up from dictionary.com. It's a figure of speech by which a locution produces an incongruous, I probably need a dictionary to first understand that, right? Anyway, the point is, look at the example. This is cruel kindness. How can one be kind and cruel together? Rush slowly. If you're rushing, how can you go slowly, okay? It's about a figure of speech where you put two opposite things in the same statement, okay? That's all. And I just extended this definition into something like, you do computing or searching on encrypted data. Okay, that's an oxymoron, okay? Which means you just encrypted the data. It is a blob of data. You can literally do nothing with it. You can't do analytics. You can't look into what it is. But you can still do some computing and searching on it. So what are those technologies or algorithms or whatever we want to call that helps us do that? Okay, so it's more like a tutorial. It's not something that I'm working. I mean, this is the area that I'm working on, but this is not going to be. I have so much of an implementation. I've made so much progress. I'm calling for contribution, and this is not a sales pitch, of course. Okay, NetApp doesn't have any products in this space. It's just me who's working. That's all. Okay, so what's the problem? I told you. I promised this. Okay, you have a user. Let's see, it's me, and I want to store some data in the cloud. Okay, that's all. Now, what I want to do, I want to store all sorts of data. I wanted to store other related information, my voter, a scan of my voter identity, my driving license, and things like that, my financial data, my bank statements, my salary statements, and everything. I wanted to store, I mean, of course, all our phone records and everything, you saw all this Apple's breaches and things like that, right? So you have phone records, medical information, videos, pictures of your cat, your selfies, and whatnot. Okay, but the problem is, you're storing it in a cloud where we're talking about a semi-trusted server because it's not a fully trusted model. The data is not on-prem anymore. It's not sitting in my laptop anymore. It's in Dropbox, or it's in AWS, or it's in Google Cloud. I don't know. It's in I don't know where, okay? So it's a semi-trusted server. Google is probably doing all sorts of analytics algorithm they have on your data, as I told you, for a simple advertisement, right? So you never know what they're doing with your data. So we're talking about a honest server, but he's probably curious. He's not going to do anything bad with your data, but you're still losing your privacy, right? You don't have privacy anymore. So that's the threat model we're talking about. I'm just going to classify all the data that we store as structured and unstructured, as all of us know. I'm going to use this later, so I just wanted to point it out right away. What is the solution if I want to secure my data and maintain my privacy? The solution is pretty simple: encrypt. Okay, encrypt all the data before I store it in cloud. Any files, okay, it could be databases, or it could be your MP3 files, or your movies, or whatever. Just encrypt. But what are we losing here? The problem is, if I want to look up something on that data, okay, if it was a database, I just encrypted my entire database. But all that I want is to run a select statement and look for, let's say, one little information, okay, you know what I'm looking for. It's a small cell in the entire table. Can I do it? Now, the database is encrypted. You can't do anything with it. Or, let's say I have a huge folder or a volume encrypted. I switched on volume encryption, and the volume is backed up into cloud. Now, all I want is a small file from it. Can I retrieve just that file? I'll have to decrypt the entire volume to get that one little file. Okay, it's probably 2 KB there, but the volume is probably running in gigabytes. Okay, so all those are problems. So if I have to look for some data, you'll have to download a lot of data, use your key to encrypt, decrypt, and get that one little data from there, right? So that's a problem. You don't want to use so much of your network bandwidth on there. And one important point that we also, that I just did not mention, was that the key is supposed to be with you as a user, right? You can't have keys there at the cloud. If you remember, rewind yesterday, do you remember something? So Google Cloud stores data so securely, they don't give away keys, they don't even use your keys. Then what keys are you using? What are the keys that you're using? Oh, they generate their own keys. Then what is the point of encrypting? You can just keep it plain. Okay, there are no keys to even encryption. How can you encrypt without keys? I had all the questions, just that I didn't ask. Anyway, so the point is, you have your key. Okay, but the problem is you'll have to download a lot of data in order to just read that one little data from there. Or another easier approach is, I can send the key to that guy. He will decrypt it for you. and then get that one little data that you want and send it back to you. But we know what it is. We don't want to do that. Yeah, so there comes this entire class or new range of algorithms called as searchable encryption algorithms. Okay, as I told you, this is a pretty new topic. The first ever thing came in like 2009, and people are still working on it. We don't have standards. There are some standards. I'm going to start with the standards and all, standard algorithms and all, because any company, if they want to sell an encryption solution, you'll have to comply to some FIPS standards, NIST standard, this one, that one, that one. Okay, so you need some standards. So I'm going to start with some standard algorithms, but I'm going to venture into areas that, even I don't understand. Okay, so the idea works like this. If I put all the searchable encryption algorithms together in one little slide, this is how it works. You have a user, and the user has the key. The user encrypts his or her data with that key, with whatever algorithm it is, and he stores it in the cloud. And when he wants to look up data from whatever he stored, he's going to run a query against that data, and that query is also encrypted. It's an encrypted query. What do you mean by an encrypted query? We'll get there, okay? But for now, just imagine that there is an encrypted query that's running, and you're going to look up for some information in that encrypted volume of yours and retrieve that one little file which is also encrypted, and you're going to get the result back. And unless you have the key, you will not be able to see the results. Okay, so that's the model. Now, speaking about security or privacy, we're talking about data at rest being encrypted. You see the big lock there? And data in motion, everything is encrypted, which means that the cloud service provider or the storage vendor is not even aware of what is the kind of queries you're running against the data. Okay? So it's even data in motion, not just the data that's being get and put, it's also the queries. Okay? Select salary from employee database where employee name is equal to Srini. Okay? Instead of Srini, it's going to be some encrypted data. So they don't even know that they're looking for some Srini's data. Okay, that's how it is. So sounds interesting, but is this practical? That's where we are headed. So NetApp pays me because they want me to make practical systems, not theoretical papers that are published in conferences, right? So I'm going to start with practical things that we can use, and then we'll get into the space that's unventured yet. So I'm going to start with an encryption mode called as deterministic encryption. So ideally, in the ideal world, the way it works is you have data, you have an encryption algorithm, you give the key, you get some cipher text. Cipher text is the encrypted data, right? The key is your handle. If you don't give the key, if the key changes, the encrypted data changes. Even if you have the same data, even if you start with the same plain text or unencrypted data, even if you have the same encryption algorithm, the safety or the key is actually the crypto key. Okay, so if you keep changing the keys, you're going to get different results, right? Now, one more addition to it. It's not just the key. There's one more variable there. The variable is what's called as an initialization vector. Okay, so the idea is this initialization vector is another variable which is going to keep changing your cipher text for the same plain text and the same key if you do it twice. Okay, so I have the same plain text. I encrypt the first time, I get some results. So I have A, I get X. I have A, I use the same key, but the next time I encrypt, I'm going to get Y, not X. Okay, so what changes is that initialization vector. If I do not have that initialization vector, or if I put that initialization vector as zeros or null, I'll keep getting the same data. Okay, so deterministic encryption is something where you have the same data, you use the same key, it will give you the same results. Okay, it's not a strong form of encryption. I'm starting with that. So it's not a strong form of encryption. So what happens is if I have some numbers here, I encrypt those numbers. You have 3, 0, 6, 5, and you see 7 and 7 being repeated. It's getting encrypted and stored in cloud. But 7 and 7, look at those last two blocks, it's the same. Okay, so the encrypted data, which is the cipher text, also are the same in this mode of encryption. Okay, in this deterministic encryption. Now, what did I say? I wanted to search for some data there, right? So let's assume some data. Let's assume this is a database and it's a column in a database, and I'm searching for count whatever. It's an aggregate query where I say age is equal to 7. Okay, that query is getting translated into count where encryption of age is equal to that little symbol. Okay, that I can do obviously. I can encrypt that one little data, right? I don't have to encrypt the entire database. The database is already encrypted there. I'm only encrypting the queries, the part of the data that I'm actually looking for. So I'm going to look for that little symbol And the cloud service provider can process that because it's going to match anyway. He's going to say that, okay, here is your answer. The answer is 2. But he doesn't know what you looked for. Was that age 7 or age 70? Right? So you have no idea about what the query is. So the cloud service provider will not be able to understand what your query was, what was the data you stored, of course he knows the results, but doesn't make any sense to him now. Right? So is this practical? Is this a theoretical model? These are practical things, and these are FIPS standard encryption algorithms. I'm sure everybody knows AES, Advanced Encryption Standard. That encryption algorithm has a mode called as ECB. Okay, ECB expands as electronic code book mode, which is not important, where the initialization factor is 0, which means you have plain text, you have a key, and the ciphertext is always going to be the same. That's all. It's a standard algorithm. I'm not smoking crack here. Okay, so and applications for it. There is a popular encryption scheme called as convergent encryption, which is used for deduplicating data. Okay, because I'm talking to a storage audience, of course we should talk about deduplication and compression and all, right? So what are we looking for in deduplication? We're looking for data that are the same. Okay, instead of having 2 copies of data, I'm going to store 1 copy of the data. But apparently I'm looking for equality of data. Okay, and can I do that with encrypted data now? Yes, of course, because I've used a deterministic encryption algorithm. I use the same key, and I'm storing it there, okay, and now I can deduplicate. Now, to take it one more step further, let me finish this. So one step further, convergent encryption, what they do is, instead of using a user key, because now the problem is, I may have a key, he may have another key, she may have another key. Now the data is going to be different, right? Instead of that, they made the key dependent on the data itself, which means that they take a data, hash the data. Now your hash is not going to be different if the data is the same, right? And use the hash as the key to encrypt the data. Wait, where is the security there? Okay, but trust me, convergent encryption is one of the deployed modes for deduplication, even in today's world. Yeah, I'll take the question.
We are making the initialization factor as 0.
Yeah.
So this is deterministic encryption, the terminology. So the question is, how easier is it to break this deterministic encryption as compared to indeterministic encryption? Like,
okay, so let me give you an example to explain that thing. So assume you have a Dropbox folder, and you're using your Dropbox folder to save all the music that you have. Okay, so you have a bunch of MP3 files. Let's assume some 200 songs, and you've stored it inside. But I don't want, and let's assume being in India, it's all pirated music, okay? We did not buy it from iTunes or anywhere, okay? It's all downloaded from some torrent or somewhere, okay? So all of these are pirated music, but now I'm paranoid that I'm storing it in Dropbox. They may find out that it's pirated music. So what I'm doing is, cleverly I'm encrypting and storing it. And to address this problem, now I have some weakness in this mode, right? So let's use this weak mode. So I've used deterministic encryption to store these MP3 files in my Dropbox account. Now, let's assume Sony Corporation goes to Dropbox and says that, okay, I have this new song that just got released a week ago. I want to see which of your users are having their song in their pirated version in the Dropbox account, okay? And I have a court order. Dropbox can't say no, okay? So they are honest, but they have to abide by what the court says. So they're going to do encryption of that particular song with the deterministic mode and search their database. We are screwed, okay? So that's the problem. You got it? Did the example work? Nice, okay. Yeah. Yeah. Now, I told you convergent encryption, where the key is generated from the hash. It's the hash. So Sony just gave you the data. They can generate a hash. Yeah. Yeah, that's right. So if you have the key, that's not convergent encryption. In general, deterministic, typically what happens is there are modes where you can brute force your keys. You have dictionary of keys and all those things. So what's called as cryptanalysis, where you look for data without having the key. They can do all these dictionary attacks and brute force attacks. I mean, everybody knows brute force, right? What was that? Replay attacks. That's a beautiful question. I was getting right there. Okay, so you can do brute force dictionary attacks, and there is a model called as INDCPA, which stands for indistinguishability of data under a chosen plain text attack. Weird security terminology, I know. So chosen plain text attack. What we just did was a chosen plain text, which was the Sony's MP3 file. Okay? And I was searching for distinguishability in that entire data set. Okay? So there are models by way of which we can actually say this is secure, this algorithm is secure at this level, that algorithm. So we need a way to actually classify algorithms and modes based on what is the level of security we give, right? So this does that. Okay, so there are models, there are very clearly defined security models to see what level of security we offer. Okay?
Question?
Yes.
Why would an application encrypt before deduplication at all?
Okay, so assume you don't have a handle on the data. I'm a paranoid customer. I'm federal, I'm government, military, I don't know, financial organization. I don't want to even give away data in plain text to the storage vendor. I'm going to encrypt it at the source, wherever the data is getting generated. Now, all that I'm saying is, okay, I'm Google. I'm going to give you discounts on the fly, okay? If you use this mode of encryption, I'm going to give you a nice discount because they're going to deduplicate at the back. So you choose your key. The key is actually there, right there, okay? So why would they use it? They'll give you a discount and you'll end up using it.
Okay. So it's more like a service that's deliberately provided to entice customers to say, hey.
All those are economics.
Okay.
Yeah, but
Thank you.
okay, so this is one mode called as deterministic mode. Let me complicate things one step at a time. I'm going to go to a different mode called as an order preserving mode. Order preservation. It looks pretty straightforward, right? So I have some data, assume integers, and I have an order to it. And when I encrypt it, they have the same order to it. Okay, so for example, if I have 0, assume this is 100, 2, 200, 3, 300, 4, 400, 5, 500, 7, 700. Okay, now it's all encrypted data. I don't know that 500 maps back to 5. Okay, but the order is preserved somehow. Even if I keep inserting more data in the middle, I'll still keep, imagine I insert a 1 there. I know that 1 is going to go right in between those first two symbols. Okay, so it's still encrypted. However, the facility that it provides is I can run range queries. So if I want to search for age greater than 3, and I'm going to search for age, encryption of age is greater than encryption of 3, I know 3 is that, and I'm going to retrieve all those other symbols and give back only those symbols, which is greater than 3, which is that, I don't know. Okay, those 3, and you have the key and you decrypt the results. Okay, this is called as an order preserving mode. So this is one step further. Initially it was just equality checks. Now you can actually run a range query. Okay, I'm just ripping one piece at a time. So as I said, this works on integers. Of course, you need an order in the plain text to actually encrypt it. It's a symmetric encryption. And an example is, again, AES has a mode called as format preserving mode, okay, some FFX mode. And that FFX mode literally encrypts your data in a specific order so that you can run such order preserving queries. Going to what's the most popular scheme called as a searchable symmetric encryption. And it's a very interesting solution. If you follow with me, I'm sure you'll be like, wow, that's pretty simple, but still it's a nice idea. I never thought about it. I could have got probably a Fields Medal. Okay, so you have data, and I just created an inverted index. Inverted index, you all know. I'm going to have all my keywords there, okay, which means that it has sensitive information about your data as well. They know exactly what the document is about. Oh, it's a pay slip. It's going to have somewhere in the document, it's going to have a number for your pay. Okay, so you created an inverted index. What we do is we're going to hash the index. Okay, hash the index just as an example. But essentially, what I'm trying to do is you use two different algorithms: a blue lock and a yellow lock. Okay, the yellow lock can be any complicated lock you want. Okay, any complicated lock. You use AES, whatever mode, whatever is the complicated mode, whatever length of key. I don't care. Okay, anything you want. But this inverted index is actually going to be encrypted with a specific mode where I'll be able to search later. Okay, so that's the second lock. Now I store those data. I store not just the data. I'm also storing this inverted index, whatever data structure it is. It may be an inverted index. It may be anything else. It may be a Bloom filter. I don't know. Okay, so what I'm going to do is to run a trapdoor. Trapdoor is basically I just leak some information there. Inverted index is leaking some information there, which is the context of the data I just stored, right? I'm going to run a query against that inverted index. So I'm calling it as a trapdoor because you know what a trapdoor is, right? So you've inserted a bug already so that I know I'll use it later. So that's it. So I'm going to run a query and that trapdoor is going to work on that data. That blue thing is the blue lock is working on that data to make sure that I'll be able to search for the data, and it's going to have a pointer to the actual data, which is already encrypted with whatever complicated encryption you did. It will retrieve that data, give it back, and then you have the key to decrypt it. Okay. Now, to make it, I mean, yeah, is he not speaking in the cloud? No. So I'm talking about that second encryption algorithm, the blue lock, as a simple hash. Assume it's a hash. MD5 hash or a SHA hash or whatever. So you have let's say an MD5 hash. Now all I'm looking for is some data in that database, right? Or database or files. Now I know what data I'm looking for. I'm going to hash that data and search for the hash instead of searching for the data. Can't I do that? I'm just running a hash algorithm. So I'm going to search for an MD5 sum, and that MD5 sum is looked up on the data structure. It knows exactly the pointer, the address, the LBA, whatever, wherever it is stored. It's going to take that up and then serve it back to you. And with a hash being a one-way function, which means that if I have the data, I can generate the hash, but if I have the hash, I can't get the data back, right? You literally don't leak anything much except the hash. So if the cloud service provider is going to do a birthday attack or the hashes and collisions and all, I mean, that's huge. Okay, but what I'm storing is actually something useless. Okay, so I don't care. So that's one mode. So it's a searchable symmetric encryption. The problem is, if I keep hitting the same data again and again and again, the cloud service provider will be able to know that this guy is actually reading that data more often than anything else, right? Because he can keep track of that access pattern. So it leaks what's called as an access pattern at the cloud service provider's premise. Okay, there's another interesting one. It's not exactly an encryption scheme, but and all of these schemes that I'm talking about, starting from the previous one, these are like 10 to 12 research papers, and it'll take how much ever time it takes to read those papers. I've just put them all in like one slide to make it easy. So, I mean, there are fine details that I'm missing here, and I think you'll have to bear with me. So what's called as an Oblivious RAM is not an encryption algorithm, as I said. So you want to store some data, and that data is like all those colorful documents that I wanted to store. And the user wants to look up that one little red document, okay? But the problem with my previous scheme was that if I keep looking at that red document, the cloud service provider will know that this guy is actually looking at that red document. He'll put in a special cloud and then somehow decrypt it for you and then decrypt for him, and then he'll see what it is. So I don't want to give away that information that that red document is the most accessed document. So what I'll do is I'll search for a green document, red document, blue document. I'm just confusing the guy, okay? That's all. That's what is called as an Oblivious RAM. Okay, so you read it, you get all the green and the red and the blue, but I know I want only red, I'll just read the red. I'll discard it. The next time I want to read the red, I'll read a yellow and a red and a blue. I'm still confusing. So that's the Oblivious RAM. And there are huge research papers to explain this concept. I just did it in 2 minutes, so please bear with me. I'm missing a lot of finer details. So the problem is, so what is that? What is the advantage? What is the disadvantage? The advantage is it hides the access pattern, of course, we just discussed. But the problem is, look at the rounds of communication they do. Okay, just to hide all these things, they put a lot of data on the network. You may have to do like 2 or 3 queries for that one important query of yours. You may have to read 10 documents for that one little document that you're interested in. So it's just unnecessarily complex. However, what people did was they combined the searchable symmetric encryption and the Oblivious RAM in order to get the advantage of that hiding the access pattern. We got the advantage of hiding access pattern, right? So they just put things together and then got that. So what it does is you have 2 locks like in SSE. SSE is searchable symmetrical encryption. You have the yellow lock, you have a blue lock. You use the yellow lock on the data and the blue lock on the data structure you used. You're going to look up the red document. Instead of looking up my red document as such, I'm going to look up the data structure for my red and the blue and the green document. Okay? Instead of the data, I'm going to look up the data structure. They just put things together, that's all. And because you just looked up the data structure, see, I've just put a pencil right there to say that it's a data structure. While when the pencil is not there, it's the data, okay? So you looked up the data structure so that it's probably a hash, an encrypted hash. I'm reading back the actual data, but again, I just confused the cloud user with all the green and blue and red and all. Okay, so it's the best of both worlds just come here. But it still has some disadvantages. Okay, it hides all the access pattern. That's an advantage. But the problem of ORAM comes here. The problem of ORAM was that communication complexity, query complexity, and all those things comes here. Okay, yeah. So that's ORAM. A much more practical thing that we can think of that that could be implemented directly is on structured data. I started with structured and unstructured data, right? So most of the data that we store, like social network data, probably the most data that we generate these days, web crawlers, maps, network routing, communication, all of these are some way or the other graph data, right? Okay, I mean, I'm just giving an example. You can have the same thing for relational data, data that's list-based or whatever, okay? Graph probably is the most complicated, so I'm just picking graph as an example. I take graph as the data set. Now what I'm going to do is, so there is a structure to the data. All I'm telling is there is a structure to the data. How can I use similar schemes on my structured data? So of course, when I say there is a structure to the data, I can split the data part and the structure part separately, right? So every vertex in that graph is probably a Facebook page. I mean, okay, so a Facebook profile. Instead of storing the entire Facebook profile in that one vertex, what I'll do is I'll store the Facebook profile somewhere, but I'll just store an address or a pointer to that Facebook page in that little structure. You got it? So essentially, I maintain the structure separately, the actual huge volumes of bulk data separately. Okay, and I have pointers there. That's all. So the same idea that we used previously, where I can use a stronger form of encryption there and a slightly weaker form of encryption here in order to go through this data structure, will still work. Okay, so let me walk you through how it works. So there's a form of encryption called as structured encryption. So all of these, anyway, you'll have the slides, and I don't know the video, but the structured encryption, you can search for these terms. Structured encryption, Google, you'll have hundreds of papers, and then you figure it out. So you have a user, he has the data, he just split the metadata and the data. The metadata is the actual structure. The data is the big bulk of the data. You used 2 locks to encrypt it. You stored all the data in the cloud. Now, how are you going to query? So you're going to query for, let's say, a yellow Facebook profile. Okay, let's say I'm stalking somebody, and I'm going to go see what their Facebook profile looks like. I'm searching for that yellow Facebook profile. And I actually am interested in friends of that yellow person. Okay, I'm not a racist, I'm just telling yellow as like a yellow, okay? So a yellow person, I'm going to search for who are the friends to that yellow person, which means that the edges that are incident on that yellow node, that's the structure, right? So if I never use this pointer. So if I'm talking about this yellow node, there are 2 edges incident, which means that he or she has 2 friends. All that I'm interested in is that orange and the green, okay? The result is going to be orange and the green. So the query is, who are the friends of that yellow person? So you'll have to get your red and the green, because or red or orange or whatever. So orange and the green back. Okay. So now how this thing is achieved is, as in the SSE scheme, you can encrypt the actual data with any complicated encryption algorithm you want. Okay. Any key length, anything you want. But the structured encryption calls for the data structure or the metadata to be encrypted in a certain algorithm where on the encrypted data, I can still do the same graph operations, right? So which means I should know what data structure I'm going to use later. So if I'm going to use a linked list, I'll use an algorithm which will support, or let's say stack, I need to use an algorithm which will do top, pop, and push on the encrypted stack. Fair enough? The same thing here. Incident nodes, incident edges on a particular node. Incident edges I mean, assuming the graph is an abstract data type, you have certain functions that you'll have to abide to, and then you say that incident edges is a function that you'll have to support if graph is the abstract data type. Okay, so all that we'll have to do is if I have the support for that on the encryption algorithm, I just use that encryption algorithm to encrypt the structured data. That's all, as simple as that. Okay, so there is something called as private stream searching. Now assume that I'm interested in let's say IPL. IPL, okay? So, but the problem, the idea is I'm going to look for news of IPL, okay? I'm a fan of CSK, so I keep looking for CSK, even if they don't play. I'll still keep looking for CSK, okay? So the point is, I don't want to give away my interest to Google. Okay, so I don't want to keep searching for CSK all the time, so that Google will later advertise to me saying that, oh, there is a CSK branded t-shirt that you may want to buy. I may end up buying, but still, I don't want that information to go away. So I don't want a stream of content, a stream like a news, like a feed, like a Twitter feed, or RSS or whatever. So how do I encrypt such stream, and how do I encrypt the queries that I hit on that stream? Okay, news is basically a stream. It keeps coming. Whatever interests me is what I'm going to click. And every click matters because those guys are actually mining all your clicks, right? So how do I do something like that? So there's something called as private stream searching. So there is a stream of content, okay? There is a stream, I don't know what it means. There are some streams. Let's assume each of it is every IPL team, okay? I'm interested in, let's say, the keyword soon and the keyword end, okay? CSK. And I don't like Mumbai Indians, so I'm searching for Mumbai Indians also, okay? So that CSK and Mumbai, I should have just put CSK Mumbai Indians instead of all this, but it's okay. So what I'll do is, I'm going to run it through an algorithm, and I generate a string of zeros and ones, a binary string of zeros and ones. I'm going to use that zeros and ones, or rather the hash, which, the binary string, to search on that whole thing, okay? And the zeros and ones essentially is, let's say it's an XOR operation. I'm going to XOR it with the stream that's coming out, okay? And that is going to result into, okay, I'm interested in soon and end, which is CSK and Mumbai Indians, and there is something which is more than zero. Anything more than zero, which means it has something that interests me, right? It has something that interests me. I don't know which one, okay? So there is newsfeed, there is a hash, and that hash is not the actual keywords that I'm searching for. It's some binary data. The XOR actually says that there is some title that this guy is interested in. Okay, I don't know which one. If it is greater than 0, I'll just return the entire stream, okay, a window of stream to the user in a document, and you read up whatever is interesting to you. You got it? I mean, there is Mumbai Indians, there is CSK, there is everything. Delhi Daredevils and everybody, but I'll still just read up only CSK. Okay, so that's the idea. So that's private stream searching. But there is a problem here. We are talking about something called as an XOR operation, right? How can I do that XOR operation on the encrypted space? Okay, so it requires an algorithm which lets you do an additive operation on that space. And that additive operation, if you do something like, I can do that one operation on the encrypted data, it's called as homomorphism. Okay, it's called as a homomorphic encryption algorithm, and this is a partial homomorphic encryption algorithm just because I can do only one operation, not more than that. Going to what was a huge trend, or rather a huge groundbreaking technology in the 2009 was what's called as a fully homomorphic encryption algorithm, which means fully supports all operations. Like what I told you about partial, supported only additive. If I can support addition and multiplication, it's fully. Okay, basically any other computation can be brought down into just additions and multiplications, and of course not, right? Ands and ors and nots, and that's what we all live on, right? So you have some data. What's fully homomorphic encryption algorithm? So you have some data, you encrypt it with some red and a green key. Red and green means public and a private key. So assume I use a red, which is probably a public key. Okay, I use the public key to encrypt all my data, store it in the cloud. Okay, it became some garbage. Of course, you can't do deduplication there, okay? That's what the problem is now. You have encrypted data, and I wanted to search for 2 plus 5. What's my result there? Okay, it could be plus, it could be multiplication, it could be anything. Okay, I want to do some computation on the data that I just stored. I'll have to translate the 2 plus 5 into encryption of 2 plus encryption of 5, which gets translated into whatever is 2, whatever is 5, and that plus is not going to work anymore because you're operating on encrypted data here. So you have an equivalent operation to plus, which is this, an equivalent operation to equal to, which is this. You get the result and give it back, and then this guy decrypts it and gets the 7 back. Okay, decrypts it using a private key and gets the 7 back. But the problem is the fully homomorphic encryption algorithm, although theoretically is feasible, we don't have a practical implementation yet. There is just one construction in 2009 by it was a Stanford PhD thesis, and that one is still not implemented by the guy who wrote the thesis. Okay, so you know what I mean. So and I tried that library that this guy is working on. I took a 1 KB file and put it to this FHE, the fully homomorphic encryption library, and that 1 KB file gave me a 100 MB result. And it took me the order of minutes So you know how practical it is. So, but the problem is there is a theoretical scheme. It's all about the computational power, and you'll just get it sometime in the future. Okay, there is a way to construct it. Yes. Okay, I'm out of time, and I have like half the presentation left. Yeah, I'll do that. Don't worry.
Hello.
Yeah. Okay, we can just move there. Okay, if you're interested. Yes.
Yeah, the question is, I think you partially answered it. Obviously, with all this encryption and the back and forth of data,
Yeah.
Do you have any data on how much additional data flows back and forth?
Yeah, so as I told, the fully homomorphic encryption is impractical as of today. Okay, it may be practical tomorrow, I don't know. But the other schemes that I told you about, right, whatever we discussed so far, all of them are practical, and the overhead is like, let's say, 1.1x, 1.1x, 1.2x, that's all. If I have a 1 MB file, I may have a 1.2 MB file as the encrypted data.
Okay, basically in enterprise environment, it will probably increase exponentially.
No. So the algorithms are the same. Even if you use enterprise data or your personal data, doesn't matter, right? The results are going to be the same.
Okay, thank you.
Yeah, thank you. Okay, yeah, I'll take the questions, but I'll just complete the presentation logically, okay? So there are several such encryption schemes. I'm not going to walk you through all of these encryption schemes, but there is one important thing that we should know, probably that's the summary for me, that these encryption schemes have trade-offs. That's the most important thing, where we are talking about a trade-off of security versus what you can do with the data, versus efficiency. Is it practically possible? Is it computationally possible? Is the storage good enough? Is the communication? So we're talking about trade-offs here, and you will have to give up on something in order to achieve something else. Okay? If you want computation on your data, which is functionality, you have to give up a little on security. Okay? You can't get everything at the same time. Okay? So I think I would conclude with this, but it has a lot more material. The slide deck has a lot more material. What I did was to put all those STE, PPE, and all of these and fare against how they come here and what is an ideal place to go. Okay? I put the same thing versus functionality versus efficiency. What is the ideal place to go? And you can walk it through. Now that you know what it is, you'll be able to read through the slides. Okay? Thanks a lot for being a nice audience. I think I'll take the question outside. Sorry. Okay. Thank you.